Hello, Professor. This is Eric Souza, and my presentation is leaf recognition. Um, so let's start off with just talking a little bit about why leaf recognition may be important. First is plant species tracking. One of the things that I found during my research was that there are currently 422,000 plant species that have been discovered, and that list seems to be growing by the year as biologists continue to discover new plants. So having a centralized and globally recognized database is important to keep track of plants and their characteristics. And some of these characteristics could include things like the name of the plant, its features, or even just helping answering questions such as is it rare or is it protected? There's some historical reference involved here, right? So having a reliable leaf recognition process will also help provide good historical context or reference to researchers and biologists. And so obviously as new plants are discovered, and they may not be new in the sense is that they're new to the environment, they just might be plants that have never been discovered before, um, it becomes important to understand how these plants affect the ecosystem. Cataloging endangered and extinct plant species is important. Um, Another statistic that I learned during my research was that a recent study uh, has revealed that botanists believe that nearly 20% of all existing plant species are in danger of becoming extinct. So if we don't catalog those species now in a somewhat reliable manner, that information could be lost forever. Location of various species, so around the world specifically. So as biologists and botanists continue to submit plant findings, we will have a better understanding of what part of the world and in what climates certain plants are able to survive. So for example, someone may find a plant in Southeast Asia, match it against a database, and learn that it's also native in, let's say, like South America. Not quite certain what value there is in knowing this, but I think there's certainly some interest from both biologists and botanists. Um, Also, assisting biologists with the large number of plant recognition requests that they get every year. Um, as I mentioned, they get a large number of requests from people to help identify plants that people have found. And uh, this whole process of identifying a plant for them currently it takes very long and it's not very precise. So having a program that's reliable and that's quick, is gonna help them out quite a bit. Um, and I mean, maybe before I move forward, I should just quickly just state a couple of key parts of a leaf that biologists are using to try to identify them. Uh, so the three main parts are the base, the stalk, and the laminina. The base is the point at which the leaf is joined to the stem. Okay, and then the stalk is that thin section joining the base to the laminina, and the laminina is the leaf blade, which is the wide part of the leaf. So just something to keep in mind in terms of like how biologists are trying to identify these leaves. And the last thing point as to why it's important is the ease of use. Right, so let's imagine that we're hiking at Walden Pond or in the White Mountains in New Hampshire, and we come across a unique looking leaf. How would we determine which plant the leaf came from? Well, if we weren't a biologist or a botanist, we probably wouldn't know what plant that leaf came from. Um, so let's imagine the person takes a digital picture of the leaf and uploads it into a program for recognition. They could almost instantly make a determination. Or better yet, what if there was a mobile phone app for leaf recognition, which currently does not exist? Then the person could instantly know the origin and the characteristics of the plant. It's a pretty neat idea, but um, I think the only real value there would be to a true nature lover. So moving along to my next slide, I'm going to start to review the. So first of all, the leaf recognition. There's one program out there that seems to be the basis for a lot of this discussion. It's called the Leaf Recognition Flavia Leaf Recognition Program. This was built or written, I think, back in 2005 or 2007 by a group of folks out in China. So I was able to find their published MATLAB leaf recognition program, uh, and it was a free download. And the purpose of this Flavia is to teach a computer to classify plants by their leaves. And so all one needs to do is to input the digital leaf image from a plant, and then with a bit of luck, the program will hopefully tell you what kind of plant it is. And then so here's the overview of the program itself. So the program utilizes the probabilistic neural network to implement the artificial intelligence process. Um, and so there were 12 characteristics of leaves. So they based it off of 12 characteristics, um, including the geometric and the morpholic features. After analysis, all 12 characteristics are then reserved, and then they try to boil it down into 5 primary principles, which are then the input vectors of the neural network. Okay, um, the system was built to recognize 32 common plants located in China and are classified by their Latin name. So for the purpose of this program only, they're really just really testing 32 specific plants. 800 leaves from those 32 plants were sampled to train this network. And I believe they use so many leaves for these 32 plants because leaves can be different sizes. They can sometimes be different shapes, and they can even sometimes be different variations of color. This program was originally designed for Linux, but I was able to find a Windows version that somebody had transitioned to. Um, and the program comes in 2 parts. The main program is a MATLAB script, and the standard JPEG images of the plants are in the second part, which can be classified by Flavia. What I thought that I would do now is try to take a crack at deciphering this neural network structure, which we had talked about in class a few weeks ago. So, during the class discussion, the professor had used some examples, and so when I saw this came from the research paper of the folks who built the program. It looked familiar from class, and I've done some reading and research on this particular structure, and I'm going to try to break it down here. So if I start with the input layer, this layer is represented by R and refers to the 5 principal variables. And remember, this program starts off with 12 leaf characteristics before finding the fewest number that represents the most common characteristics. So we start off with the 12 and end up with 5, which becomes the input layer. Okay. Then we move on to the radial basis layer. And again, R is you start with the 12 features and you reduce that to 5 with a principal component analysis. W means Q rows of 1800, right? 1800 is all the leaf images. So again, W means Q rows of 1800, Q rows or 1800 rows, and R means columns or 5 columns. So that essentially the W, and you're finding the difference between the leaf to be classified P and then each of the training leaves, which is that 1800 rows of W. Okay, and then I noticed that in this research paper, the authors state that for the characteristics of the radial base layer, that the nth element of A is equal to 1 if the input P is identical to the nth row of input weight matrix W. So I think that's what they're saying, is that you're computing the distance between the leaves to be classified in all of the training leaves. And what this radial basis layer does is it says where the leaf to be classified is closest to W, make those really high, make those 1, and where it's far away, make that 0. So I think you end up with an output with this vector A, where that's 1800 by 1, where have either values that are either really close to 1, or where the leaf is close to the training leaf, or it's close to 0, which means the leaf to be classified as nothing like that particular training leaf. So if I've broken this down correctly, I think that's how they're looking at this. And then the competitive layer is where you're going to output your 32 by one vector of values where everything is 0 except for 1, and the 1 is the particular of the 32 of the possible leaves that it could be. That's the one, and that's the competitive layer. And the competitive layer is essentially then trying to convert back the vector of A, the values close to 0 and the values close to 1, to essentially a classification, right? So the leaf name, like maple or a peach or barberry, one of the learned leaf names, and that comes out as this vector k, which is just all the zeros and then one value that's just 1. So again, that's my attempt at breaking this down. So let's take a look at the program now. And so the program is packaged like this. These are the files in the package. As I mentioned before, there's data files, and there's also files related to the program. The ones I guess to note here, this Flavia M, that's the primary source code file. Let's see, there's this PCAPNN file. That's the probability neural network program. So this contains the 12 characteristics of the plant leaves, then takes these characteristics and finds the fewest number that represents the most common characteristic, as we talked about before, and that number, as we know, is 5. This taxonomy, these are all the leaf names. We can run this in MATLAB in just a moment. I can show you how that brings those names back. What else is important here? I guess this image MD file, this is where we do the image processing, and this netGUI is what it says it is. This is just the command line version of the program, so there's no real interface there. Okay, so let's hop over to the program. Hopefully hopefully you can see this. I just launched the MATLAB program. Over here, the files, and here here's a package of files that I just explained in the previous slide. And here, these are the plants. So one thing that was kind of funny, these I downloaded. So again, it's based off of 32 plants. When I downloaded all these, I noticed it's numbered up to 33, and it took me a little while to figure out, like, why are we ending at 33 here? And it seems like that the developers are a bit superstitious and they skipped over number 13. So that's not there, but there are actually 32 files, even though it's numbered up to 33. So just quickly how this worked, I downloaded the Flavia from flavia.sourceforce.net. I copied the files to the MATLAB directory. I then had to untar it because it came in a tar format for the images. So MATLAB actually has a utility called untar, and I ran this command called untar standard leaves .tar.bs2, and that opened the package for the leaves. So maybe before I run the Flavia program, just a couple quick things of note. The taxonomy that I had mentioned before, you can look at the taxonomy here. Taxonomy NOCN, and so these are all the plant names, okay, under the taxonomy. And again, we're looking at these here, and here's 11 through 16. I mentioned 13 before, so this is 11, this is 12, here's 13. They put I am sorry in there, and I think if the recognition program comes back and can't identify the leaf, it may throw this I am sorry back at you. Another thing I thought was kind of interesting that I came across was I was able to load the neural network diagram from this program. And so load net2. Actually, you know what? I need to, I think it's actually view net2. So here we go. I thought this was kind of neat. If you remember back at my this slide here, you can see this matches up. I mean, it doesn't have the output, layer here, but the output layer we know what that is because it's 33. But here's the input of the 5 leaf characteristics. Here's the 1800 images, and then 33 again. Even though it's technically 32, this is going to be the output. So yeah. Anyways, I thought that was kind of interesting. So if I go back to MATLAB. Um, let's see. I'm going to use a Flavia command here, and I like to drag and drop this because it ensures that I'm not going to have a typo here. Um, what I need to do first is open the leaf image, and again, those leaves are in the standard image. Um, so all you want to do is select the leaf, and you open it, and then what you would want to do is you want to select the two terminals of the main and longest venation, they call it, of the leaf. So what you do is you click the points that you think are these terminals. Okay, so the terminals here, this is a pretty easy one. So here are the two, again, the longest, you want to click the terminals for the two longest venations, right, the vein here. And so those are those there. And so once you do that, you just hit enter, and it's going to go off and it's going to try to make a recognition after a few seconds. And here we go. So here's my leaf. This is the one I selected, and this is the leaf image of the plant that most matches my leaf. And so this looks right to me. And upon visual inspection, this looks to be correct, and it gives you the plant name down here. And I will say I've tested all 32 images that are in here. The programmers, the researchers claim that this program has a 93% image success rate, and I am here to tell you that that is not true. The success rate is more like 50%. So of the 32 images, I am able to get a positive match on the first try for half of them, and I've got them written down here so I know which ones they are. They're number 1. I can tell you if I select number 6. This is going to give me a positive. This is going to give me a positive match here right away. All right. So there we are. Those again, upon visual inspection, it looks correct. Here's the plant name down here. Let's just do one more because I think you kind of get the point here. So let's see. The 28 I know is one that can be recognized on the first try. There's 28. Okay, there it is. So again, visual inspection, these both look similar, and so I can assume that this plant name is correct. Let me just show you one that does not get positive result on the first try. So here we go again. I'm going to select 2 this time, plant number 2. Okay, I'm going to stick my terminals in here at the longest points, one here and one here. Let me move this down so you can see it. And then I'm going to hit enter. Okay, so this is not a match, obviously. And what's interesting is the plant leaf is shaped similarly, but it's a different color. So it's clearly not a good match there. And so this program, I think the code's a bit old. I think the idea behind it is good, but it's not. Again, I worry about its accuracy. So let me pick the number 3 here. Okay, select that and select that. Those are the longest points. Hit enter, and so let's see here. This is a match. Okay, this looks like it's a match. Visually, this looks like it's a good match here, so I can assume this plant name is correct. Let's do one more, and then I will end my presentation. I'm going to try to get one that doesn't match. Let's try 7, because I think 7 did not return a positive match for me during my testing. Okay, here and here. Okay, here's another one. So obviously, visually, you can tell this is not a match, so you can't use this as a reliable source. So that is my presentation, and thank you very much.